first time that I really did something around technical computing, it was when I was an undergraduate at Stanford. I'd come up with this really elaborate neural network model that was going to capture just how the human brain understands and can recognize letters. The night before it was due, of course, I started running my model, and it was going to take about 8 times as long as it was before the project was actually due. So I had this was my first experience in high-performance computing and clusters. I had the advantage that actually I was working in one of these large computer labs, and it's late at night, and there were a bunch of Sun workstations everywhere. So I went and I logged into about 10 Sun workstations all in a row, one next to each other, and I did the world's poorest possible man cluster implementation, because I went to each one, logged in, and started my program running with slightly different parameters on each one of those machines. And that was kind of the first time that I got involved with HPC, and it worked. I got involved in Python because I was at a Shakespeare festival in Ashland, Oregon, and I was juggling in a park in Ashland, Oregon. And while I was juggling in the park, I met a researcher from Xerox PARC, and the two of us started passing clubs. And as we were passing clubs, we started talking about programming languages, and he told me, have I got a new language for you? It's the world's best programming language. It's Python. You've got to learn more about it and get involved with it. So after this, juggling in the park, I decided I needed to go and learn more about Python. The trick was I needed to make Python as good as MATLAB was at doing sort of numerical computation, and that was a bit of a challenge. What made that really work was we had a whole community of us that worked together. It's a great open source project, and one of the joys about starting these open source projects too is that I started it was in like 1997. I spent about 2 years working on the project. Eventually, I moved on to working on other things, but there was this community around it. Additional leadership took over. Ultimately, people like Eric Jones and Travis Oliphant really took the project and took it to the next level. So I see this thing that sort of came out of this idea here that's been brought forth by all of these other people through the years, and I still get to kind of, be a part of it and, talk with these people and contribute to the design and do interesting things with it. And it kind of took on a life of its own. Whenever people ask me, what do I do for my job? Right, if I try and tell them about designing a new programming language feature, the eyes glaze over really, really fast. When I talk about doing things like helping people who are neurosurgeons to model the brain so that they can go in and do a better job of cutting out tumors, which is one of the things people did with numeric Python, or helping people figure out how to simulate nuclear explosions so that we don't have to blow up nuclear bombs in order to make sure that those that we still have around are safe for the world. I can talk about those sorts of things to people and claim the credit for what people have done with my tools. It's kind of, that's the fun thing about working on that. When I look at the large trends that are really sort of shaping where technical computing is going, I see two very strong trends, and I think they're completely at odds with one another. The one huge trend that I see is this democratization of technical computing. There's been a big push to sort of make some of this analysis of data available to a much broader set of people than it's ever been available to before. You see it in some cases in areas like business intelligence, where people are trying to apply technical computing things who've never been raised in the technical computing area. You certainly see it in science and academia. And then there's the citizen scientist side, where we've had this whole flood of data coming from the government or coming from other things about how the world works. And I think there's a very powerful movement going on to try and put the tools to analyze and understand that sort of data into many more hands than it's been possible before. So I see one trend going on of trying to really radically simplify the tools, simplify the experience so that a whole broad set of people who've never been able to understand these things before are able to in the future. You look at the trend, it goes from things like Fortran to a tool like MATLAB, to, I would claim, to a tool like numeric Python, to something like Excel, where you look at the number of people who can work with each one of those tools, and it's growing by a couple orders of magnitude each time as you simplify the experience for folks. Physics is the one science that if you look at it, we get it. We have the laws of physics. If you don't look too hard and try and understand string theory and think about what 11 dimensions might mean, we understand how physics works for the world. To the point where, we can do quantum mechanics calculations and model exactly the behavior of individual atoms. And in theory, we could model the behavior of groups of atoms. Once you start to model groups of atoms, well, you're not too far away from being able to model proteins. Once you model proteins, you're not too far away from being able to model cells. Once you model cells, Well, okay, it's just one step up to being able to model human bodies, and just another step up, and you can start to model how the world works, right? As a deep physicist, I start to see this grasp on the world. We've got these models, and we just need a little bit more compute power, right? And just a little bit more compute power. And of course, I'm totally lying when I say just a little bit more compute power, right? We need these astronomically huge amounts of computation power. So instead, people do lots of work in order to figure out how to simplify these models and come up with different things. And we do, these crazy pseudo-Euclidean, pseudo-Newtonian modeling of atoms, which instead of quantum mechanics, which seems totally wrong, and yet it's good enough. And that's it's kind of the state of the art in doing protein folding today, because we don't have enough computational power. There's a few folks who have enough computational power to use the quantum mechanics there, but there's clearly this absolute infinite capability to consume whatever computational power we can provide to folks, because what happens is the models just get more accurate. So the models get more accurate, we're able to much more to represent how things work. And if you think about the possibilities of more accurate modeling, again, just in this space of proteins, right? If we could do more accurate modeling, what that would do to the pace of being able to discover new drugs to cure diseases is just astronomical. Modeling the weather, that's another case where, again, we know the physics. We know exactly how to model the weather. You can sit down and write down the equations that model the weather, but we can't compute those equations. So instead, we come up with these approximations to the equations, and we do a lot of work to make sure that the approximations reflect the equations as well as we can. The more computational power we can make available to people, the less of an approximation we have to make, and the closer we can come to really capturing reality. And this notion that we're going to be able to capture reality inside of our computers, and what we can do once we do that, from modeling the weather to coming up with new drugs, that's what really inspires me about this space.